So we're in search of a Hermitian operator on our space of functions. And for an operator on a function, one of the first things you could guess is the derivative. That's something we know how to use. And in an earlier example with eigenvectors, I showed you that if you replaced a derivative, a function with an eigenvector of a derivative, then all your derivatives turn into coefficients, and differential equations become a lot easier. So this is set up where if we used eigenvectors of a derivative, that would be very natural for a lot of our problems. And if it is Hermitian, that gives us a whole lot of tools to work with. But for our definition of Hermitian, we have to complex conjugate it. We can do that for functions and derivatives, no problem. But we also have to transpose it. And this isn't really a vector you can cleanly transpose. So we need to flesh out the idea of transposing a little bit more. So if I have a daggered operator like this, and a bra it's acting on, one of my functions that's going to be on the left side of the integral, it's complex conjugated. This is like if that operator were acting on the vector as a ket, and then it gets staggered from how this distributes. So what we're going to say for functions is that when normally the operator acts on the thing to the right, the transpose means it acts on the thing to the left. So I'm going to phrase this as the dagger means the operator acts backwards. And we can use that when setting up our integrals and inner products. So if I normally have something that looks like this, where A is going to act on F, and then we dot product those resulting functions together, a dagger is going to go backwards, where it acts this way. And instead, A is going to act on G, give us a new function, and then that gets dotted together with F. So let's see how that works in practice when our operator is a derivative. So if I have something like this, I now know that when I am taking a dot product of functions, I'm going to integrate them. G is on the left, so it's the one that gets complex conjugated, and the derivative acts to the right. So I'm integrating G with df dx. Now, if I were to have the dagger of this, then instead it is G that gets derivatived, and then we put a complex conjugate on that, not F. And now, if the derivative is Hermitian, these two things would be equal, but we can't be sure about that yet. So we need to see if these things are equal. And to do that, we have a derivative that's on the wrong thing that needs to be moved. So I am going to move the derivative with integration by parts. This is a trick that is going to come up a lot. You might have seen it before in intermediate mechanics. If you were proving Lagrange's equation and how that minimizes the action, you're going to see that a lot in classical mechanics. So I am going to take the second equation here. It is also totally fine if I move the star directly onto G. D over dx is all real numbers, so the complex conjugate doesn't do anything to it. And so when I do integration by parts, I have g star of x times f of x for my boundary term, evaluated on the boundary, minus this with the derivative on the other one. And this right here is 0 because I told you that we're working in the space where functions on that boundary are 0. We're working with things like that. However, what we get is that we are now off by a sign of what we started with. This is the negative of the original. So the derivative is not Hermitian. In fact, it is anti-Hermitian. It is off by exactly a sign. But a sign is easy. When I dagger this, I complex conjugate it. And that would be an easy place to pick up an extra sign. So I am just going to throw in an extra I to cover for that. And this is now my Hermitian operator. I'm going to throw in a negative I, not a positive I. It's just convention. You'll see why that works out better later. So now when I dagger this, the d dx puts up a negative sign because it's transposed, and I've got to move it on to the other one with integration by parts. And the I picks up a negative sign because it's complex conjugated. The two negatives cancel, and this as a whole is Hermitian. So if I want to find the eigenvectors of this Hermitian operator, this is going to act on some function v for eigenvector, and that is going to be some coefficient that I'll call k, where all of this gives me a coefficient. If I move that I to the other side, I see that what solves this is e to the I kx. Now, these are the sets of eigenvectors of a Hermitian operator, this right here. All of these are going to be orthogonal to each other under this integral scheme we've been talking about. Now, when you first saw something like this, you probably had to prove that all these e to the I kx's were orthogonal to each other, and it kind of seemed like a lucky break. I believe that the Griffiths textbook calls this Fourier's trick, that you can use these integrals that just happen to come out to 0 or happen to be orthogonal to get information out, but it's not luck. It comes very naturally from the linear algebra system that is all running under the hood the first time you see this. So now, well, I'm overstating things a little bit here. We've got an orthogonal basis. We don't yet have an orthonormal basis. Now we're going to talk about how to normalize these and get these into a good, usable basis that we can start doing linear algebra on.